Hello there, I'm Bryan Vakiner, and I am in Professor Greco's Physics 2211 class, section MO2, and this is my video for our first physics lab, which dealt with constant velocity motion. The lab consisted of videotaping an object moving with constant velocity along a flat surface in order to examine its motion using Newton's second law. For that, I videotaped a ping pong ball rolling in the positive x direction across a table, as shown here. I chose the positive x direction in order to keep my velocity values positive throughout my manipulations. If I were to choose the x-axis in the negative direction, the only difference would be that the velocity vector would be negative. The magnitudes would stay the same. In this lab, we assumed that given Newton's second law, which is stated here, that the net force on the ball would be equal to 0. We assume that because, as shown here, you have the normal force of the table on the ball and the force of gravity, which is the earth on the ball, are negated, and the force applied is only an issue in the beginning, and we are not investigating that, and the force of friction is negligible. So given that, I took my video and put it into Tracker and tracked the motion of the ball as it rolled across the table. And from this, as you can see, I have a now linear plot on the right showing that it was in constant motion and a table given time values and position values. Using data obtained from this, I was able to manipulate a skeleton code given to us for this lab in order to predict the motion of my ball given 0 net force. I inserted the ball's mass, which is a standard 0.0027 kilograms, updated the ball's initial position vector, given the initial 0 value in the table in Tracker, and then updated the initial velocity, which would be a constant velocity because there's no external forces acting on the ball. I got this from using the difference in time frames from the Tracker data. I set the delta t to 0.01 seconds because my Tracker ran for 0.7 seconds, so at an increment of 0.01 seconds, I should get about 70 data points to compare to my Tracker data. Where I implemented the use of Newton's second law was in this part of the code where I set the fnet vector equal to 0 in the x, y, and z direction. Actually use Newton's second law here where I set the ball's final velocity equal to the initial velocity plus the net force divided by the ball's mass times the change in time. This part of the equation right here should ultimately equal 0, so the ball's velocity will not change. Given the ball's velocity and the initial position, I will be updating the position through every iteration of the while loop. Here, with the ball position is equal to the initial position of the ball plus the ball's velocity times the change in time. This line of code is just simply updating the delta t, and the rest of it is plotting and saving it to a CSV file for later. So when we run the code, we go ahead and we get a linear line just as we did in our Tracker data here, as well as a perfectly modeled motion of the ball in the x direction, in the positive x direction. Once that code is run, I was able to take the data from that and plot it against the data that I obtained in Tracker, and this is that plot. This shows that my model and my experiment matched up almost identically. As you can see, the model is the red line, the solid red line, sorry, and the experimental position are the blue dots. Any difference in the two lines can be attributed to the fact that friction is in fact not negligible. It does play an effect in slowing the ball down, but in this case, they had a pretty good relationship. So to reiterate, I investigated the constant velocity motion of a ball assuming 0 net force by taking a video of a ball, plugging it into Tracker, and tracking the data, and set that up against a computational model to determine that there indeed was no net force on the ball acting. And yeah, so there you have it. Hopefully that was informative, and thank you for watching my Lab 1 submission.